Okay, let's try problem 10.30. A 1,500 kilogram car is approaching the hill shown in the figure at 10 meters per second when it suddenly runs out of gas. A, can the car make it to the top of the hill by coasting? And B, if your answer to part A is yes, what is the car's speed after coasting down the other side? Okay, so we have a picture here. And so the car is just approaching this hill. It's going to have some kind of initial energy. And then it's going to get to the top of the hill. That energy is going to be the same. And then it's going to get to the bottom hill. And that energy is going to be the same as well. So the only thing that's going to change at these three different locations, we'll call them 1. Let me change colors here. We'll call them 1, position 1. Call this position 2 up here at the top of the hill. And we'll call this position 3 down here. So the first thing to do is we're going to orient our axes so that we call that this location down here is going to be 0. So as we go up this way, I'm going to say this is like my positive y-axis right here. So this is going to be 5, and then 5 plus 5 is 10, right? So the top of the hill over here is going to be 10 meters. So I'm saying that down here I'm going to have 0 potential energy. And up here I'm going to have my maximum potential energy. Okay, so the first question is, can the car make it to the top of the hill by coasting? And so it's going to have some kind of initial energy, right? That's just going to be its potential energy, call it U, plus its kinetic energy. And this is just going to be equal to the potential energy, right? It's just going to be mgh, mass times gravity, times h sub 1. Call h sub 1, right, because we're at position 1. Plus the kinetic energy at that point, which is going to be 1/2 m v squared. We'll call it v sub I for the initial velocity. So we plug. So we know all these values, right? We know the mass of the car. We know the gravity constant. We know the height. We know the initial velocity. So let's just go ahead and plug in. So it's just going to be 1,500 kilograms times 9.8 meters per second squared times h1, which we said is 5, right? We're just calling this our 0, and so halfway up is going to be 5. So 5 meters. That's our potential energy. Let's do our kinetic, plus 1/2. M is going to be 1,500 kilograms again. And then v squared is going to be 10 meters per second squared. Squared. Okay, so then when we plug this into our calculator, what we get is 1.49 times 10 to the 5th. This is going to be joules. Okay, so that's our initial energy. That's the potential and the kinetic energy at the first point. And remember that the sum of these energies isn't going to change as we go from 1 to 2 to 3. They're all going to be the same total. And so we were asked, can the car make it to the top of the hill by coasting? And so we know that at the top of the hill, the energy is going to be just the potential plus the kinetic energy again. But this time, our potential energy is going to be mgh2 plus some kinetic energy. And so the way we know if it's going to make it to the top of the hill by coasting is if there's any kinetic energy left. So if this mgh squared is bigger than 1.49 times 10 to the 5th joules, we know that there can't possibly be any kinetic energy, and that means that the car didn't make it to the top of the hill. However, if this is smaller than 1.49 times 10 to the 5th joules, we know that there must be some kinetic energy left, and it definitely made it to the top of the hill. So let's go ahead and let's go ahead and calculate our potential energy. So it's going to be equal to 1,500 kilograms times 9.8 meters per second squared. And now we're at the top of the hill, right? So that's going to be 10 meters. And then plus some kinetic energy, which we don't know. And this has to be equal to 1.49 times 10 to the fifth joules. So if we crank this out right here, 1,500 kilograms times 9.8 times 10 meters, we get 1.47. So this right here, just this part right here, not the kinetic energy. We get 1.47 times 10 to the fifth. And so what that means is that there has to be some potential energy to make up that last 0.02 times 10 to the fifth joules. And so that means that it definitely makes it to the top of the hill, because there has to be some kinetic energy left, because this part right here is only equal to 1.47 times 10 to the fifth. And 1.49 times 10 to the fifth minus 1.47 times 10 to the fifth is going to be 0.02 times 10 to the fifth. And that's how much kinetic energy is left at the top of the hill. So it's going to be moving. So can it make it top of the hill by coasting? Yes. And part B, if your answer to part A is yes, what is the car's speed after coasting down the other side? So we already calculated the energy over here, right? It's going to be 1.49 times 10 to the fifth joules. And so when it coasts down the other side, it's not going to have any potential energy left, right? Because it's going to be 0. So the potential energy down here is just going to be mgh, where h sub 3, where h sub 3 is 0. So this is going to be equal to 0. And so it's all just going to be in the form of kinetic energy. And so that means that all this energy is going to be kinetic energy. So 1.49 times 10 to the fifth joules is going to be equal to the kinetic energy, or 1/2 mv squared. And so just rearranging, we get v is equal to the square root of 2 times 1.49 times 10 to the fifth over m. This is all under the square root. When you plug that in, you get v is equal to 14 meters per second. So that's our speed after the car coasts down the other side. And that's problem 10.30.